Swayam Prabha. Digital India. Educated India.
Hello friends, so we are into the third lecture of our week number 8 where we are talking about the measurement of pressure. We have already gone through 2 lectures on this particular topic where we have primarily discussed about 2 very common methods of measuring pressure. One of them is manometry and other is of elastic transducers. In case of manometry, we are trying to balance the pressure force against the weight of a liquid column so that we can directly relate the height of that liquid column to the pressure. And different types of manometers we have discussed, like the simple well type and U-tube manometers, then the differential manometers, inverted tube manometers, and then a couple of ways of increasing the sensitivity of manometers, like in the form of inclined tube manometers and also micromanometers. And then in the other category where we are talking about elastic pressure transducers, there actually we are trying to balance that pressure force, or I should say we are trying to convert that pressure force, or in the terminology of measurement, we are transducing the pressure force in the form of some deflection. Like in case of Bourdon tube gauges, we are converting the deflection to the circular or angular motion of the pointer on some scale, whereas in case of diaphragms or bellows, we are transducing that pressure force into the deflection of some diaphragm or bellow, that is linear deflection. So, by converting that deflection subsequently by a second transducer into some kind of electronic signal, or I should say electric signal, we can get a direct measure of the pressure, or I should say again an indirect measure of the pressure with which all started. That is, in this elastic transducers, we basically have 2 transducing stages. In the primary stage, we are converting the pressure force to a deflection, and in the secondary stage, we are converting that deflection to some kind of electric signal, generally voltage or current. And finally, that secondary output, that is that electric signal or voltage, is directly calibrated in terms of pressure. So, today we shall be trying to see several other methods of pressure measurement. We shall be going through them quite quickly, just to get an idea about their basic principle of operation and sometimes their relative advantages or disadvantages compared to others. And then we shall be taking a look at devices which are specifically suited for measurement of either very high pressure or very low vacuum pressures. But before that, as we are always doing, let us start with a little bit of exercise. In the previous lecture, we have discussed about several numerical examples involving manometers. So, today we shall be starting with the example of a diaphragm or an elastic pressure transducer. So, just read the problem carefully, take a couple of seconds or maybe half a minute to read the problem carefully. So, here we are talking about a pressure gauge which is using a LVDT diaphragm combination. That means, it is an elastic pressure transducer, a diaphragm type, and there we are having an LVDT as the secondary transducer. That is, the pressure force gets converted to the deflection of this diaphragm, and then this deflection is sensed by this LVDT to give a voltage output. Now, this LVDT has a sensitivity of 1 volt per millimeter. That is, for 1 millimeter deflection of the diaphragm, it gives a voltage output of 1 volt, or a change in voltage output as 1 volt. The diaphragm is made of steel. The properties are given where elastic, the Young's modulus is 200 GPa. We have nu, that is the Poisson's ratio, and also the density of steel, that is given. The diaphragm is having a diameter of 20 centimeter. So, we can assume that this diaphragm is circular in nature with a diameter of 20 centimeter or radius of 10 centimeter. Now, we have to calculate the thickness of this diaphragm so that we can restrict the deflection to 1/4 of its thickness, for a maximum pressure of 2 megapascal. That is the maximum pressure that we are trying to measure with this LVDT diaphragm combination is that of 2 megapascal, and we want to design the diaphragm with such a thickness that corresponding to this 2 megapascal, the deflection which is expected to be the maximum deflection of this diaphragm is restricted to 1/4 of the thickness of the diaphragm itself. There is a second part, but I shall be coming to the second part later on. So, we are talking about a circular diaphragm type pressure transducer. We have not done any mathematical analysis of that because that will be a bit cumbersome and also not very much relevant for this particular course. But to solve this problem, I shall be using one relation straight away, which and with the objective being just to show you the importance of that relation and how to apply that relation instead of deriving that relation itself. So, here we have a relation of the deflection of this diaphragm. The idea is that suppose this is your diaphragm, the diaphragm will be hinged at both these two ends, so that it is not able to move. Let us say this is the center of the diaphragm, then r refers to the radial coordinate system, that is radial distance from the center line, capital R is the radius of the diaphragm itself. In this particular problem the diameter is 20 centimeters. So, this capital R is equal to 10 centimeter, that is 0.1 meter, and the relation this particular one, this one is giving you the deflection at a particular R location. Here y is measured perpendicular to R. So, this is the direction at which y is being measured, and at a given R location this relation gives you the measure of this deflection. We have other terms given. Here P refers to the pressure corresponding to this deflection is happening. Actually, we are using capital P, so I should use capital P for in this particular relation also. E and gamma are given, then rho refers to the T refers to the thickness this, and E and nu are given in this particular problem. So, what are the information then we know for this particular situation? Here we are trying to get a measure corresponding to a maximum pressure of 2 megapascal, that is 2 into 10 to the power 6 of pascals. We are having capital R, I have already noted capital R, then the properties are there. E is equal to 200 GPa, that is 2 into 10 to the power 11 Pascal. The Poisson's ratio is equal to 0.3. These are the informations that are required. But now look at this relation. When R becomes equal to capital R, what will be the deflection? Corresponding value of y should be equal to 0, and that is logical also because it is hinged at both these two ends. And then at which point it is going to have the maximum deflection for any pressure load, that definitely will suit when R is equal to 0. Then y should be equal to y max corresponding to whatever pressure that you are imposing. That means when you are looking for a deflection of for maximum deflection corresponding to a pressure, then for a given pressure y max should be equal to 3p divided by 16 E t cube into y minus nu square into r square whole square. Now, in the given problem we want to we were looking to calculate the maximum deflection corresponding to the maximum pressure. So, let us substitute this P as P max, and when P becomes P max, what will be your maximum deflection? That should be, we want that to be restricted to 1/4 of the thickness, and now this r square whole square can concisely be written as r to the power 4. So, if you rearrange this, we have t to the power 4 is equal to 3p max r to the power 4 by 4 E into 1 minus nu square. So, if we put the values, then what we have? We have 3 into P max as per the given problem is 2 into 10 to the power 6 Pascal, r to the power 4 is 0.1 to the power 4 divided by 4 into E is given as 2 into 10 to the power 11, and Poisson's ratio being 0.3, it is 1 minus 0.3 whole square. So, if you calculate, I have pre-calculated the final result, that will be coming as 5.1 millimeter. Please note the unit, it is millimeter, not in meter. So, we are having 5.1 millimeter, or I should say T is equal to 5.1 millimeter. That should be the thickness of this diaphragm, so that the maximum deflection corresponding to this 2 megapascal of maximum pressure is restricted to 1/4 of this 5.1 millimeter. So, this way we can calculate the thickness of this diaphragm, or in a way we can design a diaphragm for a given maximum load. Now, go to the next part of this problem, the second part of the problem, which corresponds to the secondary transducer. Here we are talking about a multi-voltmeter which we are using to measure the output voltage. So, if a multi-voltmeter capable of measuring a minimum of 1 millivolt and in steps of 1 millivolt is used for measurement, what is the lowest pressure which can be sensed by this instrument? So, we have to calculate the lowest pressure corresponding to this 1 millivolt of output. The smallest possible output that we can measure using the multi-voltmeter on the secondary output side is 1 millivolt. Now, here the sensitivity of this LVDT comes into picture, which is 1 volt per millimeter. That is, when we are having 1 volt of output corresponds to 1 millimeter of deflection. That means 1 millivolt of output will corresponds to 10 to the power minus 3 millimeter of deflection, that is 10 to the power minus 6 meter of deflection. Now, we have to calculate the pressure corresponding to this deflection. Again, the maximum deflection will correspond to the central location, that is smaller equal to 0. So, we can write this one, that is the smallest possible deflection y mean, which is 10 to the power 6 meter in this case, should corresponds to 3 into the minimum pressure P mean divided by 16 E T cube into 1 minus nu square into capital R to the power 4. Put all the values here. Capital E is given as 200 GPa or 2 into 10 to the 11 Pascal. T we have just calculated here as 5.1 millimeter, that is 5.1 into 10 to the minus 3 meter. Nu is given as 0.3, capital R is given as 0.1 meter. If you put all of them, then the minimum pressure value it is coming to be approximately 1.6 kilopascal. So, corresponding to the secondary transducer output, we can measure minimum pressure value of 1.6 kilopascal. Any pressure lower than this we can't measure using this multi-voltmeter. Remember, this 1.6 kilopascal has nothing to do with the primary transducer. It has nothing to do with this diaphragm itself, rather it is related to the secondary transducer, or not even the secondary transducer, how you are measuring the final output. If we can use a multi-voltmeter to measure the output voltage or any other voltage measuring instrument which can give you a minimum lower than this 1 millivolt, then we can go to even lower value of this minimum pressure. So, this way we can calculate for any kind of elastic pressure transducers just by knowing the relation between the deflection and pressure, like the one shown in red here. Sometimes we are also interested to know what is the frequency of this particular oscillation that the diaphragm is going to have, or I should say the natural frequency of the diaphragm, particularly if we are looking for some kind of dynamic measurement. So, this is not a part of this problem, but the frequency of this particular kind of diaphragm, this natural frequency can be also given like this, where capital R, E, nu, T all refers to the values that we have already used. Here this rho refers to the density, which is 7800 kg per meter cube for steel in this particular problem. So, you can just put the numbers in this. For this particular problem, the natural frequency will be coming as approximately 7979 Hertz. This will be the natural frequency for this particular diaphragm. So, if you have information of this deflection and natural frequency, a mathematical relation I should say, you can do the calculation for any kind of elastic pressure transducer, just like the one shown here. Procedure will remain just the same. only the mathematical relation may vary if your diaphragm is of different kind. Now, let us move to the topics that we are going to talk about today. We have already talked about the manometers, we have talked about the elastic pressure transducers. So, today let us talk about electric pressure transducers, that is transducers where the output is in the form of some kind of electric signal. Mind you, like the problem we have discussed here, here also your final output is in the form of electric signal, but still it is not an electric pressure transducer, because the primary transducer is not giving you electric output, that is only giving you deflection as the output. It is only because of your secondary transducer you are getting an electric output, and the secondary transducer is a deflection measuring instrument like an LVDT or maybe a strain gauge or those kind of instrument. So, we should not properly call it a electric pressure transducers, but there are a few examples where similar kind of situation arise and we still call it an electric pressure transducer, like the first one that we have here. Here we are talking about strain gauge sensors. Truly speaking, strain gauge sensors are not electric pressure transducers. The role of strain gauge is quite similar to what LVDT was doing in the previous slide. It is just like the figure shown here. Here you are talking about a bellow, and the operation or objective of this strain gauge is to measure the deflection of this bellow. So, again the primary pressure sensing instrument here is this bellow, and strain gauge is more part of the secondary transducer. So, this one is not a proper electric pressure transducer, this still is just the secondary transducers. Strain gauges, like we have already seen, though they are strain measuring instrument, but they generally find application in any kind of measurement. We have already seen for force, we are seeing here for pressure. We shall also be seeing similar applications for temperature or similar other measurement devices, more as a secondary application, that is some deflection is happening and then the strain gauge is picking up that deflection to give you a voltage output, which can subsequently be calibrated or subsequently be related to the primary input whatever is given, like force or pressure in this case, or maybe temperature or flow in subsequent discussions. So, this is how we can also put strain gauges on diaphragms. Like here you can see there is a diaphragm, and different locations of the diaphragm we can have strain gauges. Here we have 1, 2 and 3 strain gauges shown on this side view. If you look at the top view, there actually you can see there are 4 strain gauges located or mounted on the diaphragm. 2 of them on the periphery of a smaller circle, the other 2 on the periphery of a larger circle. There are different other orientations are also possible, but each of them is going to give you the deflection at that corresponding location, and then all of them can be summarized to get a deflection profile. That is, the deflection y as a function of r can be identified by combining these values of all these 4 readings. This is another example. Again we are talking about a diaphragm, generally for a differential pressure measurement. One side we have a high pressure P1 on one side of the diaphragm. There is a second diaphragm which is a low pressure diaphragm which have low pressure P2 on the other side, and the sensor is mounted at this particular location. This sensor is going to measure the deflection of both the diaphragms, particularly the high pressure diaphragm in this case, and then relate the distance between these two to subsequent pressure difference, that is P1 minus P2. This P1 minus P2 can be directly related to the distance between these two diaphragms, which will be done by this sensor output. This type of strain gauge pressure sensors are particularly suitable for narrow span pressure or differential pressure measurement situation, just like shown in this particular example. Next example is that of a proper electric pressure transducer, where we are talking about capacitive sensors. In capacitive sensors, we have, like in any kind of capacitive based devices, we have 2 plates, and so thereby giving a fixed capacitance. As the distance between the plates changes, the capacitance value also changes, and if we can connect these 2 plates by some kind of suitable secondary circuitry, then we can convert this capacitance to a suitable output voltage, which can then subsequently be related to the distance between these 2 plates. Like shown in this particular situation, you have a secondary stationary plate which is being subject to pressure in this particular configuration, and the other one where we have a vacuum cavity on one side, and there is a pressure sensitive diaphragm or pressure sensitive plate is having some kind of deflection, thereby changing the distance between these two plates and accordingly changing the capacitance which we can pick up from these two output ports. This is another scenario or quite similar thing, but here the plate which is being sensing the pressure, that itself is moving, and the other plate remains stationary, thereby causing a change in the distance between them, and that distance causes a change in the capacitance, thereby causing a change in the final voltage output, which can subsequently be related to this particular pressure. Capacitive pressure transducers, like any other capacitive devices, can provide very stable response because their output is very stable. Generally it is a linear response because the deflection generally is linearly proportional to the pressure imposed, and the capacitance is linearly proportional to the distance between the two plates. We are going to get electric output, which is always very easy to measure and easy to perform post calibration on it, post processing on it. Both absolute and gauge pressures we can get, like the situation shown in these two particular situation. Like here, if we go back to the first diagram, here we are having a vacuum cavity. So, what pressure it can measure? It is giving you the absolute pressure. Whereas, instead of maintaining a vacuum, if we can maintain a fixed reference pressure there, generally the atmospheric pressure, then we can get a gauge pressure reading from this. So, it can give you both kinds of measurements. However, one problem that it can face is it can be sensitive to high temperature. Also, the setup is quite complicated, particularly forming the situation and also getting the corresponding voltage output, and it can be susceptible to presence of conducting object in the vicinity, which can lead to certain kind of stray voltage as the output, which will be near impossible to separate from the actual voltage output. So, the device needs some kind of electrical isolation, so that it is not at all being influenced by any other kind of conducting object, which is kept closed. Another electric pressure transducer that we can talk about is the piezoelectric sensors. Again, the operating principle is the same like any piezoelectric devices. Here we have some kind of natural or synthetic crystal, which when being subjected to certain kind of force develops polarity, that is positive ions go to closer to one plate and negative ions get accumulated closer to the other one, and so if we connect them by a suitable output circuitry, we are going to get some kind of voltage output. So, this pressure force can directly be related to this voltage output, and thereby giving a very easy way of pressure measurement, and we can operate this device over a wide range of pressure from a quite small to quite large pressure values. They generally give a very fast response, thereby making them perfectly suitable for dynamical measurement. They are generally used in quite critical applications like measurement of turbulence inside IC engines, for measurement of blast or ballistic kind of applications. They are high stiffness, they are very rugged device, good frequency response, again providing another reason for dynamical measurement. Like this is the frequency response curve, you can see here over a quite wide range of frequency from here to this, the frequency remains very close to 0 or within plus minus 5% of 0. So, you can get any reading without bothering too much about the frequency response. If we can provide slightly larger, say plus minus 10% range, then your band gets widened even more. So, high frequency response allows us to use this kind of device for situations where the pressure is oscillating quite rapidly, like in case of IC engines. So, quite wide operating range they can provide, from small to large. We can go for measurement, particularly again very suitable for turbulence or IC engine situation, where we can have pressure fluctuating from atmospheric level to 70-80 times of atmospheric pressure. The stable and repeatable operation we can get from such piezoelectric sensors, and they provide very good linearity, but of course that depends upon what kind of sensor you are using. Quartz is a material which can provide you a good linear response, that is a good variation of the output voltage or almost linear variation of the output voltage with the imposed pressure. And finally, we can also measure quasi-static pressure, which is again very suitable in case of transient situation. However, there are quite a few factors also which are actually common in case of piezoelectric sensors, like not suitable for static measurement because like I have mentioned, may probably have mentioned in one of the earlier lectures related to the same topic, that nature always finds a way to go back to the equilibrium. Accordingly, the charges will also try to diffuse across the crystal, so that we can get back to the neutral situation, and thereby diffusing the outlet or output, or nullifying the output. So, they are not good for static measurement, but when we are looking for quite fast change in the output pressure or imposed pressure, then they are very good devices. Generally, they need expertise during installation. While mounting on a particular location, you need to be very careful and need to follow suitable procedure. They can be susceptible to shock and vibration, leading to the cracking of the crystal or some rupture of the crystal material. Requires charge amplification circuitry, because the charge that we get corresponding to general pressure levels can be quite small, and somehow you have to amplify that to get a measurable output voltage. And if they are subjected to some kind of overloading, they can there is possibility of failure of the crystal itself, permanent damage to that. So, we must adhere to the specified operating region. But still, piezoelectric sensors, like any other kind of measuring piezoelectric based measuring devices, are again very good option for pressure measurement. There is another variation of that piezoelectric sensors, which is piezoresistive sensor. Here the principle is slightly different. Here we are not looking for any kind of charge reorientation on application of pressure, rather we are talking about the change in the resistance of the crystal on application of any force. So, such piezoresistive sensors are again quite common, generally one of the earlier types of electric pressure transducers, and they again find the application in several quite common day to day applications. Their biggest advantage is the cost. They are generally quite cheap. There is a mature processing technology, because for years people are working on this, and we already have this applied in several very common devices, like we are going to see very shortly. Various levels of sensitivity we can get from the corresponding crystals or corresponding sensors. So, depending upon what level of sensitivity we want, we can choose what kind of sensors to go for. They have quite wide operating range as well. And also we can have several options for readout circuitry as well. Most common application you will find in several household appliances, like in washing machines, dishwashers, vacuum cleaners, where actually we have piezoresistive kind of sensors mounted to sense the pressure. Automotive applications as well, like gas level or oil level measurement, air pressure detection. Several biomedical applications like blood pressure measurement can be a very common example of such sensors. So, these are electric pressure transducers which are commonly applied for low to moderate and moderately high pressure applications. So far we have discussed about three different kinds of measuring technology or pressure measuring technology, out of which manometers are generally used for low to moderate pressure levels, because if you are looking for very high pressure difference, then the liquid column level will be very high. So, even with a high density fluid like mercury. So, we generally have to use manometers only up to moderate pressure levels. Elastic pressure transducers can have quite good range, like using Bourdon tube gauges we can go to quite high pressure values, but they are also more suitable for moderate to relatively high pressure measurements, whereas the diaphragm kind of gauges are more used for low pressure measurement or small pressure difference measurement. Electric pressure transducers again can have good ranges for low to relatively high pressure measurement. But now we are going to talk about another one, which is again an electric pressure transducer, but that is specifically used for measuring high pressure. High means it is really high pressure that we are going to talk about, which is Bridgman pressure gauge. Here the operating principle is probably it is difficult to understand from the pictures that I am showing, but the idea is that any common material generally have, or common resistor generally have, a pressure coefficient, like R is equal to R1 into 1 plus B into delta P. where R1 refers to the pressure at 1 atmospheric pressure, B is called the pressure coefficient, and delta P is the imposed pressure difference. Now, on application of pressure difference, certain material shows quite significant change in the value of this resistance, and that can subsequently be correlated to measure the pressure. So, as the pressure is imposed, there is a distortion causing the change in this resistance. For most of the common material, as the pressure increases, for most of the common metals, the resistance decreases, but that may not be true for all materials. Like there are certain materials for which we generally find an increase in resistance, like antimony, bismuth, lithium, these are, and a few other alloys also. These are certain common examples where we actually see an increase in resistance on application of pressure. Cesium shows a very interesting property. On application of pressure, its resistance initially decreases, reaches a certain minima, and then starts increasing. So, if we have proper idea about the value of this B, then just, and of course the value of this R1, then just by measuring the resistance R, we can easily measure this delta P. Accordingly, we can get a measurement of quite high pressure values. The pressure values can range from 0 to 1000 megapascal. So, 1000 megapascal is a huge pressure that we are talking about. So, Bridgman pressure gauges can give a very high range, but generally we use them more towards this 1000 MPa pressure levels, because for smaller pressure the change in resistance may be quite small, almost non-measurable. So, the pressure 1000 megapascal or at such a level of pressure are not measurable with the other instruments that we have discussed so far. So, they are generally reserved for high pressure measurement. Manganese in one of the common material that is generally used for measuring or fabricating such kind of pressure gauges. It comprises of 84% of copper, 12% of manganese, and rest is nickel, which is about 4% of nickel. It is one of the common materials. It generally we choose a resistor of 100 ohm under common atmospheric condition, and it has a B value of 2.5 into 10 to the power minus 11 Pascal inverse. So, the B value is quite small, accordingly we can keep on using it for quite high pressure range. The biggest advantage of this one is high accuracy of the order of 10 to the power minus 10 to the 0.1%, we can keep on using this. Then large operating range, as I have mentioned, particularly suitable for high pressures, and excellent dynamic response, so we can use them for both static and dynamic pressure measurement. But their problem is they are not usable for low pressures, because as I have mentioned, for low pressure the change in resistance may be very small without making any without causing any significant change in output voltage. They require frequent calibration, because there is chance of permanent distortion on application of pressure. So, we need to keep on calibrating it from time to time. There can be temperature related issues, because we know resistance can also change with temperature. So, it is preferable to use them under constant temperature condition, which is quite restrictive. And also another problem is that if you look to the diagram, that is why I put the diagram actually. Here around the gauge we have a fluid layer, like in this example it is kerosene oil, which is giving you the final pressure connection, or I should say the pressure is being transmitted via this oil to the gauge, and this oil itself may have certain level of viscosity, which will cause certain level of damping. So, that can lead to certain kind of error in the final measurement, and we have to make proper adjustment corresponding to that. But still Bridgman pressure gauge is a very popular device for such high level of pressure measurement. Next we go to low pressure measurement. Low pressure measurement is or we often call them vacuum pressure as well, because here we are talking about very small value of pressure well below the atmospheric pressure level, which we conventionally call the vacuum pressure. Now, as we have discussed earlier, the common unit that we use for measuring vacuum pressure is torr. 1 torr is just 1 millimeter of mercury coulomb. So, accordingly 1 Pascal is approximately 750 torr, thereby giving 1 torr is typically about 7.5 into 10 to the power minus 3 Pascal. So, 1 torr is a very small value of pressure, and here we are talking about measuring pressures which are of the level of 1 torr or even well below that. One classical instrument for measuring such low pressure level is this McLeod gauge. Now, look at the configuration that is shown here. Here we have this 2 tubes, almost like an U-tube kind of configuration, but these 2 tubes are connected to this particular line to another big chamber, which is filled with certain liquid, maybe mercury, and on top of this cylinder we have this kind of piston or plunger arrangement. Now, initially we open this particular line to the pressure which we are trying to measure, like the pressure in this case is P1 which we are trying to measure. So, as the pressure is applied, the gas which is at this particular pressure P1 is allowed to enter through these tubes. We remove this plunger, we keep open or this piston, so that the mercury can flow out of the cylinder and the gas can come in. The blue portion shows the gas, and it is allowed to enter till it occupies this particular volume, which is mentioned as cutoff volume. Let us say V is this volume, the cutoff volume is V. So, at this position we have V volume of gas occupying the blue portion of this of the tubes, and the darkish grey portion is the mercury which is still left in the reservoir. At this portion we lock the plunger, and this particular portion is also blocked. Now, in the second step we start pushing the plunger, pushing the piston, so that mercury starts flowing from the cylinder towards the tube into these 2 lines, and thereby forcing the gas to move out. Now, here the pressure remains P1 because it is still exposed to the pressure P1, and accordingly the gas gets trapped up in this portion of this vertical channel. We keep on pushing this mercury till the entire gas, which was initially having a volume of V, which was initially inducted into the cylinder, they get trapped up into the small volume of H. Now, how it is looking like? We can still visualize this one like an U-tube, because this entire portion is filled up with mercury, the entire portion below this. Here we have, if we compare at this particular pressure level, as they are a connected body of liquid, so where a pressure at this particular point refers to this applied pressure plus the pressure of this particular column of height h, this, that means the initial volume of liquid that was, or mass of gas that was inducted, the P into V, the initial one which we had, that is now having, if P is the new pressure into AT is the cross section area of this capillary tube, into H is the height, and if initial pressure was P, say P is the pressure at this particular point you are talking about, that should be how much? Following the principle of an U-tube manometer, it should be equal to Pi plus gamma into H, where gamma is rho into G, rho referring to the corresponding mercury. That means, now from the previous relation, if we take P out, so Pi refers to P minus gamma H, that is P from the previous relation can be written as Pi into V by ATH minus gamma into H, which is Pi V by ATH minus 1 is equal to gamma H, that is Pi into ATH V minus ATH is equal to gamma H. So, Pi is equal to gamma ATH square by V minus ATH. So, if I make some space on top, So, finally, we are getting Pi is equal to gamma 80 H square by V minus 80 into H, or quite frequently this V is quite large compared to 80 into H. So, gamma 80 H by V. So, this is how we generally can measure the pressure, the Pi, just by using this measurement of this gas column height H. But now you can tell me what is the principle we are using in this particular measurement. A very common principle that you have learned in school level physics. What equation we started with, that is Pi into V was the initial situation, at the end we have T into ATH, which is the final volume. What is this relation? Pi into V refers to the initial situation, the product of pressure and volume. This is the final, this is not PT, P into the final pressure, AT into H is the final volume. So, this is simply the Boyle's law. That means, we are using the Boyle's law principle in this particular example to measure this low pressure Pi. It's a can give you pressure in the range of 0.01 Pascal to 10 kilopascal. That is 0.01 Pascal refers to 0.01 Pascal refers to about 0.01 torr. 0.01 Pascal is a quite small pressure, which, and as we have seen here, 0.1 torr is about 7.5 into 10 to the minus 3 Pascal. So, 0.01 Pascal is of the order of 1 torr or slightly larger than that. So, it is in the range of 1 torr or higher, that we can measure through this particular situation. It is independent of gas compression, this particular measuring principle. Initial pressure does not matter, and also the compression by the mercury does not affect the operation. It is generally used as a calibrating tool for other kind of vacuum gauges, the very linear operation, because we are using a simple Boyle's law for measuring principle, and finally we are getting a linear relationship. Here we have the H square that I have missed. So, we are getting a straightforward relationship between this Pi and H, and no correction required. Whatever we are getting from this relation, that is the final pressure that we are looking for. However, problem is that gas should obey the Boyle's law, because that is the initial principle with which we are starting. Then there may be some kind of condensable vapor that may be mixed with the gas, and that can significantly affect the measurement. So, if vapor is present there, we have to apply some kind of corresponding correction. Continuous operation is not possible also, because we have to get the system back to the initial position before we can start another reading. So, the other one vacuum gauge that we can talk about is referred to as the thermal conductivity gauge. Thermal conductivity gauge, also often called the thermocouple pressure gauge. Here the idea is that as the pressure falls, we are talking about extremely low pressure level. When we go below a critical pressure level with reduction in pressure, the thermal conductivity of the gas also falls, because the number of molecules are less, accordingly it has much lesser capability of transmitting energy. Now, here your idea is that we have a conductor and we allow some current to flow through this conductor. As the current flows through this conductor, then the temperature of the conductor depends on three things. This conductor is surrounded by a fixed mass of gas. So, its conductivity, or I should say its temperature, will depend on three things. One is the current that is flowing through this, second is its resistance. These two combined will give you the I square R amount of heat that is being produced, and third factor is the capability of the surrounding medium to take away this heat, that is by the mechanism of convection and radiation. If the temperature is not very significant, then radiation can be neglected, then the convection or corresponding convective heat transfer coefficient, say alpha, that depends upon the thermal conductivity of the gas material, and the thermal conductivity itself is dependent upon the number of molecules of that gas. When we are talking about very low pressure, when the number of molecules are much less, actually we are talking about situations where we are below the continuum limit, that is the mean free path of these gas molecules are significant compared to the dimension of the system. In that case, each molecule has to be considered separately, and the number of molecules affect the thermal conductivity value for this. So, as we supply some current through this conductor, its there is an I square loss, and the energy produced by this will be taken care of by convection and radiation, and accordingly it will reach certain kind of equilibrium over a period of time, and the equilibrium temperature can directly be related to the number of molecules present in this, and accordingly the pressure of this gas that we are talking about. One issue is that we have to keep the radiation small, so we can use low emissivity materials, etc., so that we can have only convection as a primary mechanism. We can measure extremely low pressure from 10 to the minus 3 to 1 torr in this particular level. This gauges, one issue is that they can reach high temperature, and therefore, there is a probability for this that the gauge, that is thermocouple material itself, may get oxidized. So, we generally use some kind of noble metal like platinum, etc., for fabricating these gauges. I am sorry, I keep on forgetting exactly where I have the graphs. So, this is a typical situation. You can see when we are above this particular pressure level, then conduction is independent of pressure or thermal conductivity. Below this, the radiation becomes significant in this zone. So, the temperature is quite high we can't get the measurement, but over this range the thermal conductivity is varying almost linearly with pressure, and accordingly we can use these gauges to get a measurement of pressure using this principle. Another variation of this thermal conductivity gauge or thermocouple gauge is called the Pirani gauge, where instead of a separate heater we are using just a same filament which acts as both the heater and the sensing element. Here this filament is generally part of a Wheatstone bridge kind of circuit, just one of the 4 arms. We may have also a temperature compensating device to limit the temperature within a range. And this Pirani gauge, despite being just a variation of this thermal conductivity gauge, can give you even lower pressure, can go up to 10 to the power minus 5 torr levels. And another device which can go to an even lower pressure level can go up to 10 to the power minus 8 torr even, that is called the ionization gauge. An ionization gauge is nothing but the conventional triode, where we have a grid, we have a plate, and we have a cathode. And we have a very low pressure gas inside this, that is very less number of gas molecules. Now, this high temperature gas column, which may be somewhere in this particular zone, here they are subjected to a potential difference between this, the plate and the cathode, and when the pressure falls below a typical critical pressure level, then if we are able to impose a sufficient voltage, generally a voltage value greater than certain critical voltage, then it is able to lead to ionization. That is, the electrons will be will come out of the molecules, and as the electron passes through from the cathode towards this plate, then as they strikes the molecules, it will lead to positive ion formation by dislodging some more electrons. So, the positive ion formation actually is a result of this low pressure gas, or I should say, just to clarify, when the gas pressure is so low, that is in this particular pressure level, then we can almost assume that during its passage from this cathode to the plate, there is not too many molecules for the electron to cause more than one collision. So, the number of positive ions produced can then directly be related to the number of molecules present there, accordingly the pressure inside this cylinder. The value of Vc, which is also called the ionization potential, that varies depending upon what kind of material you are using. Like if you are using, say, something like cesium, for cesium it is just 3.88 volt, which is probably the lowest we can have, whereas something like helium, which it is about 24.6 volt. It is the maximum among the monoatomic gases. If we are using some kind of diatomic gas like hydrogen, oxygen, etc., it is typically of the order of 15 volt. So, we have to impose a voltage higher than this ionization potential, and also you have to ensure that the pressure is lower than certain critical level. then this ionization gauge can easily give you a measurement of pressure, a very low vacuum pressure as shown here. So, there are a few other kind of gauges as well, like Knudsen gauge is another name that is coming to my mind as a vacuum gauge, but generally these are the most common one for which I have just described the principles. So, this takes me to the end of this particular module, where we have talked about different ways of measuring pressure. We started with a discussion about pressure versus stress, then we talked about different kinds of pressure like the static and dynamic pressures, absolute and gauge pressure. Then we have spent a significant amount of time discussing about manometry. We talked about elastic pressure transducers. Today we have talked about electric pressure transducers, several kind of electric pressure transducers like the piezoelectric and piezoresistive devices, capacitive sensors, etc. Then we have talked about the high pressure measurement, that is only the Bridgman gauge that we have talked about. There are a few other options, but not that popular. And then we have talked about three different ways of vacuum pressure measurement using the McLeod gauge, ionization gauge and thermal conductivity based gauges. So, that is the end of pressure measurement. I would like to thank you for your attention for this particular week, and also would request you to send me the queries whatever you have, so that I can immediately respond and clear your confusions. In the next week we shall be talking about the measurement of flow and fluid velocity measurement. Thank you very much.